we will have our last talk called on OpenNetLab from Professor Byung-Gon Chun. But Byung-Gon actually he has a class to teach today, so he provide a recorded recorded video for us. And the first author of this paper, Zhang Yong, actually she can answer the questions in the QA session. The professor actually is from SNU. He is a full professor in the computer science and the engineering department in Seoul National University, and he is also a CEO at Friendly AI, whose mission is to make large-scale AI simple for the enterprise. So now I will play the recorded video from Professor Byung-Gon Chun. And by the way, so sorry for this. Professor Xu Hong in the talk 6, he has some family emergency, so he cannot make it. But if you are interested for this talk, maybe you can contact me. I can send you some information on his talk. So the talk 5 will be the last talk in this workshop, and after this talk, we will start our panel discussion.
Thank you for inviting me to Microsoft Research Summit 2022. Hi, I'm Byung-Gon. I'm currently a professor at Seoul National University. I work on systems for AI. I am also a CEO of Friendly AI, which is a startup that provides cloud service for training and serving generative AI. Today, I'm going to talk about OpenNetLab, an open platform for reinforcement learning-based congestion control for real-time communication.
I think I need to.
This is joint work with the Microsoft Research and Microsoft production teams. Most of the credit of this work goes to my wonderful collaborators listed in the slide. Real-time communication has shown great increase during the COVID-19 pandemic. It is everywhere in our life, from online education to remote work in the forms of video conferencing, live commerce, and live streaming services. In 2025, RTC traffic is expected to become 17% of the whole internet video traffic, and each market will become over $200 billion worldwide. In RTC, WebRTC is the de facto open standard for web-based RTC. WebRTC serves as a backend for mainstream web-based RTC applications. Specifically, it has a transport layer tailored for RTC with video and audio capabilities exposed to applications with easy-to-use APIs. RTC tries to optimize quality of experience, in short QoE. The figure shows an overall control logic in WebRTC that determines QoE. Given video and audio frames, the codec compresses them into bit stream, which is sent to the internet by pacer. The bitrate of the pacer is adjusted to follow the target bitrate set by the congestion controller. After receiving the data, the receiver sends packet-level statistics, such as packet loss or packet delay, with regard to the received data. Based on the stats, the congestion controller identifies congestion signals and determines target bitrate for the codec and pacer. Here, the congestion controller is the key enabler of high QoE. The role of the congestion controller is correctly identifying congestion signals and perform bitrate adaptation. If the congestion controller overestimates available bandwidth, sending excessive amounts of data leads to congestion, incurring packet loss and delay that lead to QoE degradation. On the other hand, if the congestion controller underestimates available bandwidth, WebRTC downgrades video quality based on the reduced bandwidth, which again leads to unnecessary QoE degradation. Currently, a widely used congestion control algorithm for real-time communication is the rule-based Google congestion control algorithm. This is the default in WebRTC. The rule-based congestion control algorithm consists of rules. The rules consist of predefined conditions and bit rates. Based on the observed packet level state, such as loss rate and packet delay, the algorithm triggers rules that adjust the target bitrate based on predefined conditions. The rule-based congestion control algorithm has clear limitations. As these rules are predefined, it fails to adapt to the patterns that deviate from the rules. To overcome these limitations, the reinforcement learning-based, in short RL-based, congestion control algorithms have been proposed. Instead of the hardwired mappings, they learn to adapt actions based on observed performance results. Because of their learning-based nature, they enjoy flexibility, as they don't have any predefined assumptions, and thus can adapt to newly observed patterns. OpenNetLab is an open platform that is designed to support RL-based congestion control for RTC. This is a community effort including over 10 schools located in Asia. For RL-based congestion control for RTC, researchers need fast training and testing on the real network path. OpenNetLab meets these requirements by providing two environments: fast training on a simulator and testing on the real network path on the open testbed. First, our trace-driven simulator has an easy-to-use interface and adopts a simulator-in-the-loop design that combines WebRTC and NS3. Second, the OpenNetLab testbed includes diverse network types, including cellular, wired, and wireless, which are necessary to cover various network conditions. Let's take a look at the simulator first. Using our simulator, an RL agent can iteratively collect experiences online by interacting with an NS3-based simulated network environment. Specifically, our simulator includes NS3 that replace outperform probe traces. The WebRTC sender sends video traffic to the environment and collects network statistics such as throughput, delay, and loss rate from the WebRTC receiver. This is used as a state for the RL agent, and the agent returns an action which is the target bitrate used by the sender. Users can develop their RL agent with an easy-to-use Python interface, which allows easy porting of widely used RL libraries such as OpenAI Gym or Ray RLlib. Our simulator allows fast and reproducible simulated network environments with NF3 and achieves high fidelity simulation by including the full stack WebRTC sender and receiver. Now let's talk about the real network testbed. To test a trained RL-based congestion control algorithm, researchers can select the sender and receiver nodes in the OpenNetLab testbed, considering the network type and characteristics, for example, bandwidth range and mean round-trip time. The sender node uses the trained RL agent to perform congestion control. The nodes in the testbed are coordinated by a group of back-end microservices located in Beijing. The following shows the steps involved when one uses the OpenNetLab testbed for testing. First, users submit a code of trained RL agents through the OpenNetLab web frontend. Then the frontend sends the code and software packages required to run it to the deploy manager. Deploy manager maintains states for job information such as user and model ID, and the status of the job, such as waiting, running, finished, and killed. The deploy manager consults resource manager, which maintains states of all physical and virtual machines in the testbed for allocation or release of virtual machines to run the job. As deploy manager schedules jobs to the selected testbed nodes, the status of the job is sent to the deploy manager. When a job ends, the deploy manager returns the virtual machine to the resource manager. A notable use case of OpenNetLab is MMC's 2021 Grand Challenge on bandwidth estimation. In this challenge, the participants used the OpenNetLab simulator for training their RL agents. OpenNetLab contributed to the research community for training and testing state-of-the-art RL-based congestion control algorithms. Gemini, a challenge winner, and HRCC, which is published as a full paper in MMC's 2021 conference, perform widely used the rule-based baseline GCC in both network and video quality metrics on the low and mid bandwidth network path. As a next step, we are expanding the horizon of OpenNetLab by supporting more environments and RL algorithms for training. In online RL algorithms, agents learn from online interaction with the network environment during training. Currently, OpenNetLab supports simulated network environments for online interaction. By supporting training on emulated and real network environments for training, users can try environments with different fidelity training time trade-offs. In addition to traditional online RL, OpenNetLab plans to support offline RL, where agents learn from a fixed data set of trajectories during training. A key enabler for training performant agents through offline RL is a large-scale trajectory data set of diverse congestion control algorithms collected from real network environments. As an open platform for RTC, which runs congestion control algorithms submitted by researchers, OpenNetLab is a natural place to collect and maintain large-scale trajectory data of diverse congestion control algorithms as a community resource. To summarize, I introduced OpenNetLab, an end-to-end open platform that supports RL-based congestion control for RTC. It provides experimental environments ranging from simulation to the real-world network testbed. OpenNetLab tools are open source in GitHub, and researchers can join OpenNetLab through the official website. Let's make big impact on RTC together with OpenNetLab. Thank you for listening.
Thank you, everyone. So I think we have a very small QA session for this talk. So do you have any questions? So Zhongyong, are you online?
Yes, I'm online.
Yeah, I actually have a question for you. So I think a very important thing is to make the testbed and evaluation reproducible. So do you have any consideration when you do this work?
By reproducible, do you mean that the environment being reproducible, right?
Yes, and also if we have for example, if we have one algorithm and maybe today we have a rank, yes, and maybe after 1 year we also have a rank for this algorithm. So is that possible to make the two ranks are consistent to to make everything reproducible? The rank is reproducible, the algorithm is reproducible.
I think because the RL agent, training an RL agent as a congestion control algorithm assumes that the actions are stochastic. So the state action reward sequences cannot be completely reproducible. But I believe that we can train a performant RL agent that can outperform other algorithms with the right design and training strategies for the RL agent.
I see. Thank you.